Hey, welcome to Integral Calculus Part 5. We're doing some more integration here, and this will be the last one where we're just doing integration for integration's sake. We're actually going to look at applications from here. So let's start with the fundamental theorem of calculus again. We've been doing a bit of this right at the beginning, and now what we're going to say is we're still doing the same thing. We want to find the antiderivative of f of x. That is the function here f such that its derivative is f of x. So we're coming back from a derivative back to the function. Okay, so if the function is continuous, that means it's not undefined anywhere there, and you keep drawing your rectangles if you like, then the definite integral of f of x is this. This is a fundamental theorem. We're going to work out that function value at b minus at a. That was the area given function. Remember the sum of all the infinite rectangles there of height f of x and width delta x. We took the limit of that to get this expression for the sum of the infinite number of rectangles. And then we evaluate. You might say, well, Huddy, there's nothing new there, but here's something new over here. Come over here, the definite integral. Why is it a definite integral? Well, if you've been doing the exercises in the presentation, you'll be realizing that when we write integral of f of x dx, we get a whole family of functions, don't we? We put plus c. Now with the definite integral, of course, both f of b and f of a would have the c in them. Do you get what I mean? When we put in, let's say we're using this, let's put f of b in there, or b in place of x. That would be that one minus f of a. So there's no c in there when you do this subtraction. You didn't realise that at the beginning. But when we've gone into this notion of a whole family of functions, then our antiderivative f of x is really fx plus c. And it's not definite, is it? It's a whole family. But when we evaluate it across an interval, the c's would cancel out, and so it becomes a definite integral. So that's a little bit of background there for that name. It's still the fundamental theorem of calculus, though. Okay. Well, let's have a look at a slightly different way of setting the problem out. Here it is here. When we've found the antiderivative, we're going to put a b up the top and an a at the bottom to signify we're doing this. Usually we do this step and then substitute the numbers in. We don't usually write that in our working out. So that's a slight change in arrangement there. All right, so let's have a look now at going on and looking at the implications of this. So come on down to this next screen here, because I've got a red hot burning question for you. It's red. Okay, so does this definite integral always give the area? Let's examine this over here. This says the integral from neg2 to 3, so it's the sum of an infinite number of rectangles of height x cubed, this is the height. Well, it's not strictly speaking, it's a limit of the sum as n tends to infinity, all that stuff, but it's reminiscent of this, isn't it? It's an infinite rectangle sum, a height by the width. So does it always give the area? Let's look at the graphical implications of this statement here, because I've gone on the Casio and Shift F5 to go to GSolve and chosen this option. Okay. So, what do you reckon? Across the interval from neg2 to 3, do you see any difficulties? Let's have a look here. What do you notice? Hang on. The heights of the rectangles are downwards like this. The heights would be negative. So you'd be summing up a negative height by the width. Hey, this would give a negative area. Oh, what about here? Oh, this is okay. They are all up like that, and that would give a positive sum, a positive area. So if we did it without considering that, straight across the interval from neg2 to 3, what would we have? If we call this area A1 and this area A2, the overall answer, A2 would be positive, but we would be subtracting the value from A1. A1 would be negative. Effectively, our definite integral, okay, from the fundamental theorem, would give us a difference in the areas. Okay, so what's the answer to, does it always give the area? No. We have to check the graph, that some of the heights are not negative and producing a negative total there. But of course, if we just went willy-nilly across the interval and just did this, maybe we'll do this, let's do this in the new notation. X to the fourth on 4, evaluated from -2 to 3, is 3 to the fourth on 4. Take -2 to the fourth on 4, which is, what's this, 81 on 4, so that's 20 1/4, minus, now this is -2 to the fourth is 16 on 4, so that's -4. Our answer to our definite integral is 16.25. That's what the calculator's got up here. And we could, you know, in a silly way, just say that's the area, square units. But it isn't now, is it? It's actually A2 take A1, because we can see with the graph that some of those rectangles have negative height. So the definite integral is correct, 16.25, but it does not equal the area from -2 to 3. So here's an interesting twist to the fundamental theorem. Sound all right, and it was good, but we have to come up here, check the graph. Okay, so when it asks for a definite integral, this is this one here, then you have an answer down here always. That answer is correct, but it's just whether you make the implication that it means the area under the curve. Do you get it? You might think about that. All right, well, let's go and have a look and see what you think about doing some of these. So I've brought this up again. This is from Hayes Publications. These are the rules for definite integrals. To prove these is not actually in the course, and you don't have to be able to manipulate them as such, but I think they're important to realise what you can do. So if you're integrating from A to B of a function, then it's minus the integral from B to A. Okay, so that's important. So you're reversing the direction, if you like. And if you're integrating C times a function, you can put the constant out the front there. And if you're integrating from A to B of a function and then from B to C of the function, you can just integrate from A to C. You don't have to split it into two. Just remember, we are not saying necessarily that these mean the area anymore. We've got to check the graph, okay? But we might not be asked about area, in which case we'll just work out the number. Okay, the integral from A to B of f of x plus g of x, you can split it into the integral from A to B of f of x plus the integral from A to B of g of x. You're allowed to split them up that way. Okay, so keep those in mind. They're handy in being able to work out definite integrals of varied functions. Okay, so let's come down now and have a look at some examples. These are from Hayes Publications, their standard level book, 3rd edition. Okay, so we're going to do this one here. So what do? Right, let's state it. Then let's do the integration, the antiderivative. Increase power by 1, divide by the new power. 2, increase power by 1. So 2x over 1. And then this is our new notation. We're going to evaluate it from 1 to 3. So that means we put 3 in first, minus 1 in. Work out the numbers. 3 cubed on 3 is 9, plus 6. Use of brackets is very important because that subtraction is there. Brackets, so what's that? And then we've got a third plus 2, and we would work that out. So it's 15 take 2 1/3, which is 12 2/3. Okay, little step in there that you'd have to do. All right, do you get it? We're not doing anything really different. We're just using this box notation, which is conventional, rather than f of 3 take f of 1. Let's come down then and have a look at another one. We're going to go right through a group of functions so you feel comfortable with them. Integral from 0 to pi on 3 of sine x. Let's do that one. State the problem. Get the antiderivative of sine, which is neg cos. Remember Hutty's little rule. Sine is friendly under differentiation because the derivative of sine is just cos. No sine, no plus or minus problems there. But cos is problematic under differentiation because the derivative of cos is minus sine. Coming backwards though, because it's the antiderivative, sine is not friendly under integration. You've got to remember to put in the negative. Okay, and then evaluate it from 0 to pi on 3. So it becomes neg cos pi on 3, take f of b, take f of a, neg cos 0. And this is very, very important to remember the values of the key angles here, and that's definitely part of the syllabus. The cos of pi on 3 is a half, so this is neg a half. A cos of 0 is 1, so it's neg 1 or plus 1. Okay, so the answer is a half. Notice we're not calling them square units. We don't know whether that does actually represent the area from there, under there. Now, I might have a look at that in a minute with you. So let's have a look at this one. Okay, integrating, increase the power by 1, 2x squared, divided by new power, the 2 would go out. So I left out that step. And 3 lots of 1 on x, integrated is 3 ln x. And since x is greater than 0, we don't need to put the modulus because we're only evaluating it from 1 to 4, both positive values. So let's do that. Put in 4, x squared is 16, plus 3 ln 4. Take always f of b, take f of a. 1 squared is 1, plus 3 ln 1. Okay. And so here, what is that now? 3 ln 1, the log of 1 is 0. The power you raise e to get 1 is 0. So it's 16 take 1, that's 15. What have they done here? This is interesting. 3 ln 4 would do, but let's investigate 3 ln 4. It's actually equal to 3 ln 2 squared, which is log of a power is the power times the log. So it's 3 by 2 ln 2, which is 6 ln 2. So you've got to be able to do that. You wouldn't actually have to change it in this problem unless they said right in terms of ln 2. Okay, let's do the easy one here. Let's come back over here and have a look at the graph of sine x from 0 to pi on 3. You know that sine has a maximum, and we'll just stop that there for the minute. So if we plot that maximum, and we're coming up like this, is up to, oh, that's pi on 2, so we're going to pi on 3, which is 2/3 of the way. Okay, somewhere like that. Oh yes, that's all from 0 to pi on 3 is all above the x-axis, so that's okay. Okay, so that's going to work all right. So this would actually be the area from 0 to pi on 3. Okay, so we have to check that, but we don't have to. If they just give us these problems up here, the definite integral, we just come up with a number. Okay, it's only if they ask us for an area implication that we call it square units or talk about that at all. Okay, come down. In the course, in this IB standard level course, they can give you functions which you cannot integrate with the work that we do in this course. There is further integration, obviously, but here, for example, you cannot, with the tools we give you in this course, integrate this. Why? Because there is no obvious function that's when differentiated gives this thing. Okay, so we don't know how to do the antiderivative of this. Okay, and there's no rule that's been applied that we can spot. No, you have to go to the calculator, and here's the calculator. I've expanded this a bit because we might look at it a little bit differently from that. The TI and the TI in SPI, if you've got those, you can check those out. Let's have a look at doing this function from run mode on the Casio. So you go to run mode, here it is here, and then you go options, so you have to hit options and get this window, and then you hit calc. Okay, and up comes, there it is, the integral, so you'll hit F4, and then we get this up there, and you can just enter the numbers. Okay, so enter the function and just scroll around with this key so you highlight the various vacant spots there, and then you get the answer coming up there. Okay, so that's run mode on the Casio. Run mode, then hit options, calc, choose integral, okay, and fill the function in. Let's have a look at in graph mode, because this is interesting, particularly if you're looking at the relationship between the definite integral and the area. So go to graph mode, plot the function, okay, then what we're going to do is go shift F5, which is GSolve in there. Up comes this window, and what you want is on the next page, so you need to hit F6, and on that last page there's the calculation you want. So here you have to hit F3, and then you need to enter in the numbers. So entering in 3, when you get to this window it'll come up 3 as your lower. If you hit execute, oh sorry, we haven't done that yet, that's what was up there, so it come up lower, and then if you hit 2 it'll enter the lower bound, and then that registers as a lower bound, and then if you hit 5 that window will come up and it'll draw it from 2 to 5, and you can actually check out that none of the graph is below the axis. So the actual answer to this definite integral, here it is here, the definite integral, that's the answer. And if somebody said, does that mean the area under the curve? You've got a picture here and you can say yes. The definite integral of x e to the x dx is definitely, was it 2 to 5, is equal to 586 approximately. And if we wanted to say what the area was, yes, the area is equal to this, okay, because all the rectangles have positive heights there, and we are summing with that definite integral an infinite number of rectangles. Okay, let's have a look then at some problems for you to have a go at. Okay, so this is from Hayes Publications, and just go through using questions 1 to 4 to check the definite intervals, check the properties of definite integrals here. So they're saying do each one and just relate them, okay, the negatives and so on, and see if they are equal. Part A is checking these should be what? These should be the negative of each other, and so should these. So just go through and see how it all works. Okay, go down and have a look at those, and then I'll show you the answers afterwards. Let's go down to question 5. Okay, evaluate the following, check with your calculator. That's very, very important. I would check with your calculator twice, with run mode and also graph mode. Okay, 5, 6 and 7. Let's have a look at 8. There's a technology one. I do want to mention 7 because the only way of doing that, you don't know what the rule of differentiation gave that, so you have to change it to something simpler, as we've seen before. Okay, so you use a half, take a half, cos 2x there. Okay, just remember with integration it implies the antiderivative, so that implies reversal of a rule. Okay, a rule of differentiation. If you can't find that rule, like in this one, sine squared, you don't know what rule produced sine squared, you have to change it to a function whose parts are identifiably produced from a rule of differentiation. So just remember that. What rule produced this? That's the idea with this integration. Okay, evaluate using technology in question 8. Do it 2 ways. Okay, pause the presentation, have a go at each of those. And let's come down and just finish them off, I think. So look there. 11 is an important one. It's connecting what we've done before. Integral from 0 to 3 and 3 to 7. Does it mean the area, and can you work it out? Not with the integral because you haven't got the function, but you could work out the areas in the sections and so on here, couldn't you? Okay, area approach. Okay, so instead of working out the definite integral, you're going to work out what it would be looking at the diagram. Just keeping in mind, if it goes under the axis, what are you going to talk about there? Might have to adjust the sign there. Okay, so 11 and 12 are like that. 13, 14 and 15, and 16 down there as well. So have a look at those. Using some of the definite integral properties there. All right, let's have a look at the answers then. Here's some answers for you, through to 16. Let's check you're able to do those. Well, I've got one other little thing for you here, and that's this is arguably in, whether it's in the course, some books include it, some don't. And this is evaluating each definite integral where we are reversing the chain rule. Okay, the chain rule. A couple of clippings here come from Pearson's. So here we are, the integral from 0 to 1 of this. Now we've got to get the antiderivative of this. Do you remember the earlier work? Let u be the function of which the other term is the derivative. So du by dx is 2x. So it looks good to go. We've got du by dx and we've got u in here. So it's going to become integral of u cubed du. Now Pearson's done a little bit of a naughty here. When you change to u, you should change the limits of integration. Right, because u is 1 plus x squared. Okay, so it should have been over here, it should have been 2 and 1, because if you put x is 1 back over here in here, 1 plus 1 squared is 2. So the limits of integration in u land is 2 and 1 if you're going into the variable u. So it's u to the 4th on 4. Okay, can you see that? I'm going to do this in a different way in a minute because this confuses some people. When you go just into u's, you must change the limits of integration because u is not x, it's x squared plus 1 there, or 1 plus x squared. Now we can evaluate it. U to the 4th is 2 to the 4th on 4, and then evaluate that'll be 4. Take 1 to the 4th on 4. Okay, so that's that. And then we have our usual answer. So you can see the problem. If you need to use substitution, it can get confusing with the limits of integration. Okay, so I suggest when you have a problem like this, I would not make it a definite, or I'll change it to this. I'd go this way first, rewrite the function, and integrate it. And so using u, so I'll just put in here, let u equal 1 plus x squared, du by dx, let's put under there, is 2x, so that's okay. So this integral equals integral of u cubed du by dx. I'm putting that one first, then that one du. So I'm doing it as a separate problem almost. This is the integral of u cubed du from what we said before, which is u to the 4th on 4 plus c, which is 1 plus x squared on 4 to the 4 plus c. So I'm doing it as a separate indefinite integral. Now let's look at what I'm going to do. I've run out of pages here, but what we'll do over here now, which should be underneath, is integral from 0 to 1, therefore, of 2x by 1 plus x squared cubed dx, I'm going to change it. It equals 1 plus x squared to the 4th on 4, which I'm taking from over here, which I've worked out separately, so I don't have to change the limits of integration. All right? I'm staying just in x land in my definite integral. So I'm doing the definite integral after working out by substitution what the antiderivative of this function is. So, etc. And then you just sub it in. So you might like to choose what you do here. What you must be careful of if you're using this method, if you realise that these limits change here, because you're working just in u and you're not returning to x land. Okay, so here I've gone and returned to x, and then I can keep the x limits here. So make a choice and see what you think. All right, so let's have a look then at what we're going to do next, and we need to go to applications next. Okay, but before we do that, I'm going to take you down to a good summary set of problems from Pearson's and have a go there. Okay, so here's a good list of definite integrals for you to have a go at. So I want you to try to do all of these, and the solutions are down below. Now let's just scroll down there. We'll bring up 15 and 16 and down to 20. Okay, so have a go at all of these. You'll notice here we've got some which are integrable by substitution, so you might separate it, integrate it, get it back in x land, and then substitute the numbers in if you like. Okay, so see how you go with that. I'm going to go down and show you the answers now. Okay, so there we have them. Just check. This is the TI calculator. You'll have to check that if you're using a Casio. Okay, that's down to question 5. Let's come to question 6 there. 6 through to 9. That's checking your answers. And then 10, 11 and 12. We'll come down to 13 and so on in a minute. Okay. 13 through 15. And that's part C of 15, so I'll leave 15 up there. Oops, hang on, just come back here. 15 and 16. Slips there. Okay. And 16 through 18. And then 19 and 20. All right, so if you can do all that, you've got great skill in integration, and what we're going to do is see what we can apply it to, which is going to be of use. And there's kinematics problems coming up, and some areas as well, all very interesting stuff. Okay, so have a go, and I'll catch you later on. Cheers for now.